In this module, we're going to discuss geometric Brownian motion. Geometric Brownian motion is a very important stochastic process or random process that's used everywhere in finance. We have the following definition. We say that a random process xt is a geometric Brownian motion if for all t, xt is equal to e to the mu minus sigma squared over 2 times t plus sigma wt, where wt is a standard Brownian motion. So we've discussed Brownian motion in a separate module, so you can look at that module if you like to remind yourself what a Brownian motion is. But one thing to keep in mind with a Brownian motion is that wt has got a normal distribution with mean 0 and variance t. This is one of the properties of a Brownian motion. We call mu the drift, sigma the volatility, and write xt tilde gbm mu sigma. An interesting observation to make is the following. Let's take a look at this expression, but let's replace t with t plus s. If we do that, we'll see that xt plus s equals x0, and in fact I should have had an x0 here. So xt plus s equals x0 e to the mu minus sigma squared over 2 times t plus s plus sigma times wt plus s. And now what we can do is we can rewrite this expression up here in the exponential. We can subtract a minus wt and add a wt here, and we can break this summation up into t times this plus s times this. If we do that, we get this term here on the right-hand side. But what's interesting is that this quantity here is actually equal to xt. So we can write xt plus s equals xt times the exponential of mu minus sigma squared over 2 times s plus sigma times wt plus s. And this representation is very useful. It's in fact very useful for simulating security prices when those security prices follow a geometric Brownian motion. This quantity here, wt plus s minus wt, well, that's just a normal random variable with mean 0 and variance s. Moreover, it is actually independent of xt, and this follows from the independent increments property of Brownian motion that we discussed in that other module on Brownian motion. So that means, for example, suppose that we wanted to generate values of a geometric Brownian motion at time 0 and at time t, but also maybe at these intermediate times, maybe delta, 2 delta, 3 delta, and so on. Well, what we can do, so we want to generate x delta, x2 delta, x3 delta, and so on. Well, what we can do is we can actually simulate the geometric Brownian motion at these time periods by just simulating n0 delta random variables. And that's very easy to do in standard software. You can even do it easily in Excel. So you could generate a sample path of your geometric Brownian motion or a sample path of your stock. You start at time 0 with x0, which you know, and then you get x delta using this formula here with t equal to 0 and wt plus s minus wt, well, that's just equal to a normal mean 0 variance delta random variable. So that would give you x delta. You could then get x2 delta by taking t equal to delta and s equal to delta. So you will get x delta plus delta is x2 delta. That's equal to x delta times this quantity again here. And again, to generate this term, you could just generate a standard normal random variable with mean 0 and variance delta. So it's actually very useful for simulating a geometric Brownian motion. And we may return to this again later in the course. Here's the question. Suppose xt is a geometric Brownian motion with parameters mu and sigma. What is the expected value of xt plus s given little t? Well, from equation 10 on the previous slide, we know that xt plus s is equal to xt times the exponential of this term here. Well, at time t, all of this is known to us, so we can take this outside the expectation, and we're left with this times the expected value of e to the sigma wt plus s minus wt. Well, this term here, as I've already said, is normal with mean 0 and variance s. So all you're trying to do when you compute this expectation is actually compute the moment generating function of a normal random variable. And we've seen that before. Suppose z is normal with mean a and variance b squared. then it implies that the expected value of e to the s times z is equal to e to the as plus a half b squared times s squared. So this is the moment generating function of a normal random variable, and we can just use the standard result up here to recognize that this must be equal to e to the sigma squared over 2 times s. This term cancels with this term, and we get this expectation equals e to the mu s times xt, so that the expected growth rate of xt is in fact mu. Here are some sample paths of geometric Brownian motion. The important thing to notice with these paths is that they are continuous, they are very jagged. If I was to zoom in, I would still see that they are very jagged, and they are continuous, as I said, so they do not jump. I can draw any one of these paths by keeping my pen on the page. The following properties of geometric Brownian motion follow immediately from the definition of Brownian motion. Recall that we saw the following. So we know that xt plus s is equal to xt e to the mu minus sigma squared over 2 times s plus sigma times wt plus s minus wt. Okay, so what are these three properties? Well, the first property states that these ratios, xt2 over xt1, xt3 over xt2, and so on, they are mutually independent. And that follows because if I divide across here by xt, I can see I've got the only random variable here is this increment, and the independent increments property of Brownian motion will actually imply this first property here. The second property is the property I mentioned on the previous slide. That is that the paths of xt are continuous as a function of t. They do not jump. The third property states that the log of xt plus s over xt has got a normal distribution as follows. And that also follows from equation 10, which I've rewritten here. So I can easily see that the log of xt plus s divided by xt is equal to, well, it's just this term up here in the exponent. It's equal to mu minus sigma squared over 2 times s plus sigma times wt plus s minus wt. This guy is normal with mean 0 and variance s, and so this quantity is normal with mean mu minus sigma squared over 2s and variance sigma squared s, which is exactly what we have here. A couple of observations about geometric Brownian motion. It is clear, number one, that if xt is greater than 0, then xt plus s is always positive for any value of s greater than 0. And again, let's write out equation 10 here just to see this more clearly. So this is our equation 10 from an earlier slide. We can see that if xt is greater than 0, then of course the exponential of this will be greater than 0, and so xt plus s will be greater than 0. So if we are using a geometric Brownian motion to model stock prices, then we can see that the limited liability of a stock price, i.e. the fact that a stock price cannot go negative, is not violated. Another observation is that the distribution of xt plus s divided by xt only depends on s and not on xt. In fact, this was clear from the previous slide where we had this result here. The log of xt plus s is a normal distribution, and this normal distribution does not depend on xt. It only depends on s and the parameters mu and sigma. And this is nice because we wouldn't expect returns to depend on xt. So we can view this as being the return on a stock, the return between times t and t plus s, and we don't expect in general that this return should depend on the current value of the stock. So again, this is another nice property that geometric Brownian motion has that is generally reflected in stock prices as well. So these two properties suggest that geometric Brownian motion might be a reasonable model for stock prices, and indeed, geometric Brownian motion is the underlying model for the famous Black-Scholes option formula that we will also see in this course.